Yeah, thank you. Thank you for, first I need to thank the organizers to offer me such a opportunity here. Today I will do a little investigation here if someone has ever used the Numpy. Yeah, you can. Okay, most of you. Yeah, so today I will talk about our new project, open source project Mars, which is a tensor-based unified framework for large-scale data computation. Yeah, it's quite a long name. And I will introduce myself. I'm a senior software engineer at Alibaba, and my main job is combining the big data with the Python language. And recently, I focused on Mars. Yeah, this is the topic. And I used to develop a library called PyODPS, which provide a pandas-like API, and it can run on the big data platform developed by Alibaba called Max Compute, and it can also run on the database like Postgre or MySQL. It can also run on local with pandas. So what is Mars? What can Mars do? Let's start from an example. Our mission here is to estimate the pi with Monte Carlo methods. Monte Carlo methods is actually very, very simple. It's statistical methods. It utilizes a range of numbers to perform the simulation. Here we have a circle with radius 1 and enclosed with a 2x2 square. Here we generate a large number of points, and the points can be within the circle and also can be within the square. So we can conclude that the points within the circle divided by the total numbers is actually the area of the circle divided by the area of the square. So we can conclude that the pi can be the number of the points inside the circle divided by the total numbers multiplied by 4. So one important thing is that the more points we generate, the more accurate the pi will be. So the simple idea to solve this problem is that we can write a pure Python version, and here we assume we generate 10 million points, and we just need a loop to, in each iteration, we can generate the x and the y, which is the coordinates, and if the distance from the point to the origin is less than 1, we can increase the inside the variable with 1. And we can get the pi is actually quite close to the real one, and the execution time is about 10 seconds. It's actually quite slow. For such a numerical mission, the NumPy is always a good choice. So we can implement such a mission with NumPy. Here we use the numpy.random.uniform to generate the n by 2 the random data, and the data squared by 2 is actually will do the square root to all the elements in the 2-dimensional array. And then we will sum on the axis equals 1, which is do the sum on the row direction. And here we will get a 1-dimensional array, and we'll just do the square root, and if all the one-dimensional array is less than 1, we just sum them up, and we will get the total number of points within the circle. So with NumPy, we can get a astonishing time that we can accelerate the pure Python code with over 10 times faster. So is there any way to accelerate the code of NumPy? The answer is yes. We can use a library called NumExpression. NumExpression is a numerical expression evaluator for NumPy. You can just fuse a few NumPy operations into one operation. So you can just accelerate your NumPy code, and you can tell that the execution time is 25 times faster than the pure Python. So I want to introduce you a really, really fantastic library called CuPy. You know, with the emerging of AI applications, the GPU like the NVIDIA is becoming more and more popular nowadays. So the CuPy is a library that you can just write exactly the same code of Numpy with simple import replacement. You can just make your code run on the NVIDIA CUDA GPU. So you will get the astonishing time to over 270 times faster than the original Python. So it's really, really fantastic project. By the way, the CuPy is just a side project of deep learning framework called Channel. So I have mentioned that the more points we generate, the more accurate the pi will be. So let's just scale up the data to 1,000 times larger. And here we generate 10 billion data. And we will get the memory error because we cannot generate, we cannot have so much memory. And if you are running on the Jupyter, you will get a worse situation that your kernel is killed by the system or other process. You will get the dead kernel, and you will lose all your data you have run. It's a terrible. So your face may look like this, but the life has to go on. Yeah. So the problem is quite simple. Yeah, we can handle the 10 million scale, so we can iterate 1,000 times, and in each iteration we handle the 10 million problem. So yeah, we iterate 1,000 times, and we will get the time is just the 1,000 times to the Python to the NumPy version. So yeah, we just leverage one CPU core. That is the problem. Nowadays, our computers are all multi-cores, but we just write the code can just only leverage only one CPU core. So the problem is actually mentioned in the picture that is one CPU is very, very busy doing the computation, but the other just doing nothing actually. So we can conclude that only small subset of NumPy operations can natively be parallel. For example, only the tensor and some stuff can leverage multi-cores. It will utilize the multi-cores internally. Except that most of the operations cannot be parallel. So we may consider the multi-threading or multi-processing to figure it out. And if one computer's resource is limited, we may consider the distributed program to handle the large data. So here we can implement the multi-threading version of the Monte Carlo methods. Here we write a function, and in the function we handle the 10 million scale, and we create a concurrent futures thread pool executor with concurrency 4. It's just has a thread pool with 4 threads, and we just submit the function 1,000 times, and yeah, we just wait for the futures to finish. And we can see that the execution time is up to about 2 times. And thanks to the elegance of the concurrent futures library, it's an internal library of Python, and we can just modify one line of code from the thread pool executor to the process pool executor, and we can tell the execution time is up to 3 times. So let's consider some more complex computation. Here we create a random matrix 100,000 by 100,000, and we do the A dot the transpose of itself, and we minus A, and at last we will do the standard deviation. So I think maybe some of you has forgotten the dot, which is very useful in the linear algebra. Yeah, the input data is about 75 gigabytes, so it's quite large. Most computer cannot handle the data. Here we have the matrix A and the matrix B. The matrix C is calculated by the A dot B, and the blue element in the matrix C is calculated by the row of matrix A and the column of matrix B. Actually, here we do the okay, never mind. So so we can imagine that if we want to implement the parallel version of tensor, it's quite hard, let alone the entire computation. So so estimating pi with Monte Carlo is easy to reach parallel, but many tasks are hard to implement the parallel version manually, and it's even harder to make the execution distributed. So what framework do we need? So first we need the familiar interface, just like the Numpy, and we can do simple import replacement. And the third thing is we need the scalability. Even on our laptop, we can leverage multi-cores to perform the computation, and we can scale out to thousands of workers to do the calculation. And we can leverage the modern hardware, just like the GPU, to do the acceleration. And we are in memory computing, but we support scaling the data, the intermediate data, which we not use later, which we'll use later, and we just spill it to the disk or some external storage like S3 or something, and we can just make our computation proceed. So this is all about our project Mars, and currently one of the most important component is the Mars Tensor, which is which provides a Numpy compatible API and to process large ndarrays. The ndarray is called a tensor in our scope, and we currently have covered 70% of commonly used interfaces of Numpy. And we can run Mars Tensor on a single machine on our laptop with threaded or local cluster schedulers. Local cluster is the full runtime of the distributed, and we can run Mars Tensor on thousands of workers to perform the computation. This is the brief of the implementation interfaces, like the tensor creation. We supported the Numpy swans, empty zeros, and ones like something like that. And we support all the random sampling functions in Numpy, and we support basic manipulation like S-type, the transpose, and broadcast too. And we support all the aggregation function in Numpy, like the sum, max, and something like that. And we support the indexing, like slice, Boolean indexing, but we currently partially support the fancy indexing and something like that. And we support the FFT module in Numpy, and we support the linear algebra like the QRSVD Chomsky decomposition and some like. And we also support the matrix multiplication, like Benjamin has mentioned. So with Mars Tensor, you can imagine that you can have a smooth transition from Numpy to Mars Tensor. Here is just the code we have written. The input, I have to emphasize that the data is about 150 gigabytes. It will may cost the OM. So the Mars Tensor code is, you can just import mars.tensor as empty, and the other code is identical to the Numpy, except for we have to call the execute method. Yeah, so Mars Tensor is actually a lazy execution framework. And the benefit is that we can just optimize all the process as many as we can. So you can tell that the peak memory usage is only about 1 GB. So the Mars tensor can save as much memory as possible. And the execution time is quite close to the handwritten multiprocessing version. So someone may ask the execute is quite annoying. Sometimes I just want to develop the code. I don't want to call the execute every time. I need to be aware of that, and that's fine. We also provide a mode called eager mode. In contrast, the graph mode is the default mode. It's born for performance, but if you want to develop your code just for developing and debugging, you can leverage the eager mode. So here is a code, example code. Yeah, we can from the mars.config import options, and we can enable the eager mode, and then we'll create a tensor, a one-dimensional tensor from 0 to 9. When you represent the tensor, you will get the data, and when you call the a.sum to perform the aggregation, you will get the final results immediately. Except for the Numpy part, we also extend the ability to the GPU and the sparse spots. Yeah, if you want to create a tensor on GPU, you can just assign the GPU with true. Is so the tensor when it comes to the real execution, the tensor will be allocated on the GPU, and the upcoming computation will also happen on the GPU. So just one line of code modification. So for the sparse, yeah, the real world data is mostly sparse. Here is the example that we create the I, which is a matrix with 1 on the diagonal and the zeros elsewhere. So if we store the data with the sparse encoding, we can save as much storage as we can. So we can just create the tensor with sparse equals true. So you can just make the data encoding with the sparse. So how Mars actually make everything parallel? There are three important components. First is the computation graph. Yeah, just like all the data flow systems, we have the computation graph to represent the calculation. One difference is that we have a tile process, just which turns a tensor level graph into a trunk level graph. I will explain that later, and we will schedule the trunk level graph to multi-cores or the distributed runtime. Here we just write the code. We do nothing, but only generate the tree, the tensor expression tree in the memory. Here we have two kinds of expressions. The first is the blue one, which is operand, and the orange one which is tensor. So with the rand operand, we create a tensor A, and with the add operand, we create tensor A plus 1, and with the sum operand, we created the tensor B. So we just record this in the memory. We actually do nothing. When the user called the execute method, we will serialize this tensor graph to the JSON or protobuf. Yeah, it's the serialization, and we will serialize. We will submit the data, the serialized tensor graph to the scheduler to do the tile work. So tile is very simple. Yeah, you just split the data into chunks. And for example, we have 1,000 by 2,000 tensor. assume that we specify the trunk size 500 on each axis. We will split the tensor into 2 by 4, that is the 8 trunks. For each operand, we support the tile for all the operands we have implemented. So the trunk graph may look like this. Here we can tell that if we only have 1/8 of the memory, we can also perform the calculation. Yeah, we can just do 8 times. Yeah, and if we have 8 cores, we can just make the computation run on the 8 cores. So that is why Mars can save as much memory as we can, and also we can make everything in parallel. But the trunk graph will not be executed immediately because we need to do some few stuff. Yeah. So here for the 3 operands, we just fuse them into one. On the CPU side, we leverage the num expression that I have mentioned to fuse the operands into one operand. And for the GPU side, we leverage the CuPy's element-wise kernel or some stuff like that. So let's get back to the complex example that I have mentioned. So let's see how Mars generates the actual computation trunk level graph. So you can tell that it's quite complicated. For the scheduling, there are 2 main key points that is very, very important. The first is how operands with no inputs allocated to workers impact huge on performance. Here we assume that we have the first and the 2 operand connected with the 5th operand, and the 3rd and 4th operands connected with the 6th operands, and assume that we have 2 workers. And if we allocate the 1st and the 3rd onto a worker, and the 2nd and the 4th onto another worker, the whole computation will not be efficient, because we have to fetch the data from one worker to another worker and calculate on the subsequent computation. So if at first we allocate the 1st and 3rd, and the 1st and the 2nd on a worker, and the 3rd and the 4th on the other worker, the computation will be efficient enough. So this is the first key point. And the second key point is that the operands with big depth should be executed first. Here we assume given the same example, but we have only one worker. And when we execute the 1st and the 2nd operand, at this time, if we schedule the 3rd operand, the execution will not be efficient, because the 5th is not executed, and the memory generated by the 1st and the 2nd operand cannot be released, because the 5th need them. So if we execute the 1st and the 2nd, and we schedule the 5th operand, it will be more efficient, because we can just release the memory generated by the 1st and the 2nd operands. So the scheduling is really, really complicated in Mars, but this is the 2 basic key points that we can apply to make our scheduling more efficient. So during the whole development, we were facing a few difficulties. The first is we adopt the classic master and workers. Yeah, we have a master to coordinate all the computation, and the workers just do the real computation. So the master could be a single point. That is, if the master failed, all the computation will be failed. And the second is due to the infamous Python GIL problem. How to release the worker? How can workers release GIL to? Because most of our computation is CPU intensive, so that's an important topic. And the third is the master could be, the logic of master could be extremely complicated, and how we can decouple the components to make the code neater and understandable. So our answer is actors. Yeah, I will briefly introduce the actor model. It's just a conceptual model for concurrent computing. Here, the circle here is just the actor. You can have millions of actors. Each actor can have a mailbox. It can accept mail from other actors, and it can also send mail to send a message to other actors. And each actor can only process one message at the same time. That's important because you don't have to worry about the concurrency. Each actor has its internal state. But for Python, there is no de facto actor model library for Python. Not like the Erlang, which its internal support for the actor, and for the Java or Scala, there is a library called Aka, which is very famous for the actor. But there is no de facto actor model library for Python. But we consider that we only need a lightweight actor model framework, and the actor model framework is internally used by the Mars schedulers and the Mars workers. We don't expose the actor to the users. So we just can implement a lightweight actor model framework from scratch. And the second is Mars distributed, including the schedulers and the workers, are based on the Mars actors, like I said. And we implement the Mars actors with G-event. And yeah, we are actually backend irrelevant, so we can support the async IO backend in the future. This is the architecture of Mars actors. We can have a bunch of thousands of workers just connected with the network, and on each machine, the user can start the Mars actor pool with specified the sub-process. Here we assume that there are 3 sub-processes, and the sub-processes are connected to the main processes with pipe. And there are 3 important components in the main process. That is the socket handler. Each machine can receive message from other machines via the socket handler. And the second important component is the dispatcher. The dispatcher should be aware of the entire sub-processes, and he should know which message should be sent to via the pipe, because it knows where an actor allocated on. And the third important component is the shared memory. We just leverage the arrow plasma to do the shared memory. And on each subprocess, we just leverage the coroutine of G-event to handle the message on an actor dot on receive message will just handle one message. So if one actor wants to send message to another actor, there could be 3 conditions. The first is the 2 actors are on the same subprocess. So that's quite simple. We just put the message into the queue, the mailbox of the other actor, and it's quite simple. The second situation is the 2 actors are allocated on different subprocesses, but they are on the same machine. So the message could be serialized and sent to the dispatcher via the pipe, and the dispatcher will know which subprocess sent to, so it will send the message to the destination. The third is that the actors are allocated on different machines. So we can send the message to another machine via the socket, G-event socket, and the other machines, the dispatcher on the other machine will be aware of the message and send it to the destination. So we can implement the Monte Carlo methods with handwritten actor model. So actor is just a class. So you can just implement one function, that is the onReceive. So we write the trunk inside actor to process the 10 million scale, and we create an actor to create 1,000 trunk inside, and just let them do the calculation. And here we create actor. We can specify the address parameter. That is, you can create an actor on another machine if you specify the address. So we can tell the execution time is even faster than the multiprocessing version. So our Mars actors is quite efficient. So all the Mars distributed are built on the Mars actors. So we can leverage multi-cores. We can release skill because we are multiprocesses, and we can easy to write the distributed program because, yeah, they are just classes. We can just decouple our logic into many classes. And thanks to the I/O performance, we have the great I/O performance thanks to the coroutine. Yeah, this is just the advantage of the coroutine. And like I said, we're easy to decouple logic into many classes. So Mars schedulers can be multiple because we can just create the actors on different machines. A few schedulers can connect with the consistent hashing, and we can create actors on different machines. So the schedulers will never be a single point. And the Mars workers can maintain a queue, and if the scheduler want to execute a trunk graph, it can send the graph to the worker, and the worker will put it into the queue and execute it according to the priority. And we also support the fault tolerance. That is very important because if one worker is down, we don't want the whole computation fail. So here is we can look at the life cycle of a task. Here we assume we have one client and 3 schedulers connected with consistent hashing and 5 workers. The client can create a session implicitly or explicitly, and it will create a session actor on the first scheduler according to the consistent hashing, and then the user executes a tensor. The tensor will be serialized and submitted to the session actor. The session actor will create a graph actor and distribute one scheduler. And the client will be aware of the existence of the graph actor, and it will wait for completion and just pull the graph actor. Yeah, and the graph actor will, at the same time, the graph actor will just tile the tensor graph into the trunk graph. And here we assume we have 3 operands. So we create 3 operand actor and distribute to different schedulers. And the first and the second operand will find that they have no dependency, so they can just find the best worker to execute. When one operand finish, it will notify the subsequent operand. And when the first and the second operand are all finished, the third operand will be aware of that, and he will choose the best worker to execute the subgraph. And here we assume the data on worker 5 is larger than the worker 2, and the third operand will decide to compute on the worker 5 because we can fetch less data, and then it will perform the computation. Here the client will be aware of the finish, and it will fetch data from the graph actor, and the graph actor will fetch the data from the worker and to the client. So the client can execute other tensors. Here we do some simple benchmarks, and for the first benchmark is embarrassingly parallel benchmark. Here we create a tensor, and we do the +1 and multiplied by 2 to all the elements in the tensor. Here the red cross is the NumPy on a single machine, and the blue line is the Mars, and the green line is Mars, and the blue dot line is the ideal execution time. And we can tell that even on a single worker, the Mars can be a few times faster than the NumPy, and with the workers increase, the execution time can actually reach the ideal situation. And we continue to make the data larger, and we just do the same computation, but at last we will sum them up, and we can see that the input data is over 100 gigabytes. So NumPy cannot do the computation, so Mars can still reach quite a good parallelism. So our project is open sourced at github.com/mars-project/Mars. Yeah, our code is completely open sourced, and all our development happens on the GitHub, so you can track everything on the GitHub issues and the GitHub the pull requests. The second link is our docs, and our project is pretty young. We have just open sourced for 4 months, so but we have received over 1,300 stars. So if anyone are interested in our project, it's welcome to open issue if you find any bug, and to join our community and contribute code. At last, I will briefly introduce the roadmap. So the first thing is that the community means a lot for us. So for this year, one of the important job for us is to build the entire community. We want to get involved more people to join our community, to join the development. For the development, we want to add more implemented APIs of NumPy and SciPy to the Mars tensor. And the second part is we want to distribute the pandas, just like we distribute the NumPy, which is called the Mars data frame. We just mimic the pandas API, and this is working in progress. And the third part is we want to make the distributed scikit-learn, the XGBoost, and so forth. And the fourth part is we want to make everything distributes just for the Python functions and the Python classes. You can create a function on the remote machine, create a class on the remote machine, and do the Python just run the Python code without considering the distributed runtime. And like I said, we support serialization to the protobuf and the JSON. Actually, they are language relevant, so we can support multiple languages, not just Python. We can support other languages, but I will look at the requirements from our customers or users and see what will happen. So thank you for coming and your time for.
Okay, thank you very much. And no mistake there. You will need to choose the best question.
Okay.
And yeah, we have the first one. No.
Okay, thanks a lot. It was really interesting. I had a question. Do you plan on making any kind of visualization tool for a graph, like TensorBoard for TensorFlow?
TensorFlow, yeah, actually, any operand can be here. For now, the operand executed on the worker is actually NumPy. but it can be any library like TensorFlow or something. When we come to the Mars remote I have mentioned, yeah, you actually can write a function. Within the function you can write the TensorFlow or something. It can run on different machines.
No, I meant like
okay.
You have a graph of
Uh-huh. Uh-huh.
and I meant like it would be useful for people to have a visualization tool that could help them understand what
Okay.
what the scheduler, how it configured the graph generation
Mm-hmm.
process.
Yeah. You mean the yeah, TensorBoard or something like that. Yeah, we have a web UI to illustrate the computation, but for now it's not so completed and it's not so fancy like the TensorBoard. But we are working on it. Yeah.
Is it open sourced already?
No. We actually are developing it. So.
Okay.
Thanks. I'm curious, have you done more like complicated benchmarks like multiplying large matrices? Because like adding is pretty obviously parallelizable, but if you have like matrix million by million, which doesn't fit in GPU memory, latency communication would kill all the speedups.
Yeah. So your question is about the benchmark. Yeah, actually we have a real computation that the data is extremely huge. It's let me think. It's about 1,000 billion or hundreds of billions elements in the tensor. It's a huge tensor dot another huge tensor, and we leverage over 200 workers to perform the computation, and we can just accomplish the computation in about 2.5 hours. But we didn't compare to, we just compared to the big data platform of our company. We defeat them, but we didn't compare to other libraries or something. Yeah, we will do it in the future.
Hello. Thanks for a great tool showing us. I have 2 questions. The first one, were there any tests for finding the extreme points where Numpy is faster in the beginning of small batches of information and when Mars becomes faster?
No, can you just...
when we run Mars, we also run additional infrastructure to support its work. So, are there any tests did you done such as to understand when NumPy on small pieces of data is faster than Mars, and when it's better to switch to Mars implementation?
Okay.
And the second one, have you tested Mars on low-powering devices, Raspberry Pi, for example? Is it also showing such great performance as on big PCs, or it can have some problems with running additional infrastructure?
For the first question is how can we know the Mars tensor can be faster than the NumPy, or the NumPy can be faster than the Mars tensor? When the data is small enough, it's definitely faster for NumPy, but it's complicated because there are so many different operands, and we can just give you an accurate answer to that. But maybe someday we will do the simple. Maybe someday we will try and see what will happen. And can you just repeat the second?
The second was, have you tried to run it on low-power devices like Raspberry Pi?
Raspberry Pi.
Yeah, some sort of this.
Okay. No, we haven't.
Hello. Can you tell more about fault tolerance and about how a network works in the top of...
I didn't mention much about the fault tolerance because the time is limited.
I'm sorry. In addition to fault tolerance, is it work both on CPU, multiprocess mode, and GPU?
Oh yeah.
Yeah.
The multiprocess, we have two levels of fault tolerance. First is we have multiple processes on one single machine. So someday a single process may fail because it's killed by somebody or some. Yeah. So we will just refork the process and rebuild all the actors on it, and we'll just do the computation because everything is stateless in the process. So we can just compute the failed job again for the process.
Refork with same data, right?
Yeah, the same, because if it failed. And the second level is the worker level. Yeah, if one worker is down, we will find which operands are running on the workers, and we will mark them as fail. And we will reschedule to find the dependency. If the dependency is also lost, we'll mark it as fail again, and we will reschedule all the failed operands to other workers to make the computation continue. Yeah, I don't know if I have answered your question.
Yeah. Thank you.
No, yeah.
So what is about non-numeric data processing? Will be it implemented in the way the pandas do, or in another way?
Pardon me?
What about non-numeric data processing? Will be implemented in the way the pandas do, or not?
The question is about non-numeric data types and processing it, and are you planning to implement it?
Will it be implemented at all?
Will it be implemented at all for the numerical task?
Okay.
Yeah.
But maybe for synchronizing with pandas.
I don't quite get to your question, and I think the Mars tensor is just it's the counterpart, the distributed counterpart of Numpy. If you can implement an algorithm with Numpy, or you can just implement with Mars tensor, but you have to look at the interfaces to check if it is implemented by Mars tensor.
Okay, thank you.
Okay.
Okay. Any more? We have time for the last question. Yeah. Okay.
Hello again.
Yeah.
I have a question about the graph of computation. Is there a way to control a graph itself? Let's say I have some graph and I want to modify this to some my needs. Is this possible?
Currently, we don't provide the way to modify the graph to the users. But if you are interested, you can modify the Mars runtime or something to modify it. If you are interested in.
Okay, thanks.
Okay.
Okay, thank you. Thank you, Chris. Okay. You should choose the best question.
For tolerance.
Okay, fault tolerance. Okay.